Welcome. This tutorial is related to the regular solution model. In the regular solution model, we wrote that the change in enthalpy delta H, or in our case that is the same as delta U, is some regular solution parameter omega times XA, XB, where XA and XB are the mole fractions of A and B atoms. So, we want to know what is the relationship of this omega, the regular solution parameter, to the crystal structure and the bond energy. So, that is what we are going to derive in this tutorial. Again, this is taken from Introduction to Thermodynamics of Materials, Gaskell. This derivation is not given in Porter and Easterling, this derivation is not given, it just refers to Gaskell. So, from Gaskell we are going to do this derivation. So, we are going to assume that the Avogadro number, so I am going to take a mole of material. So, the Avogadro number I am going to denote by N naught. So, XA, which is the mole fraction of A, I am going to say is given by Na by N naught, and XB, which is the mole fraction of B, is going to be given by Nb by N naught, and I am going to assume that XA plus XB is equal to 1, which implies basically that Na plus Nb is equal to N Avogadro. In other words, we have only A and B species, nothing else is there. So, the lattice is either occupied by an A atom or occupied by a B atom. Now, let us say that suppose I have a lattice and I have these A, B atoms. Okay. So, this is A, so this is B. Okay. So, I have this distribution. Then I want to know what is the energy, and I am assuming that all the contribution to the energy is coming from the bond energy. So, that is the approximation we are making. So, let us say that all this is coming from EAA, EBB and EAB. These are the bond energies. Suppose if I take two A atoms and from infinity if I bring them together, they are going to form a bond and that bond strength is A. And if I take two B atoms and bring them together from infinity towards each other, then they form a bond and that bond energy is BB, and AB atoms form the bond AB. So, what is the total energy? Then that energy E is nothing but probability of finding an AB bond EAB plus number of EAA bonds plus number of BB bonds. So, if I take the total number of BB bonds multiply by the BB bond energy, total number of AA bonds and multiply by the AA bond energy, total number of AB bonds and multiply by the AB bond energy, of course, I will get the total energy. Okay. Now, let us say that in my crystal structure Z is the coordination number, that is the number of nearest neighbors that are there in my structure. So, this is 6 for cubic and 8 for body centered cubic and 12 for face centered cubic and so on and so forth. Okay. So, these are the total number of nearest neighbors, and in terms of their bond energies we know. So, if I want to know how many bonds are associated with A atoms, of course, there are Na A atoms and Z is the coordination number. So, that will be the total number of A bonds, because if I am having A atom here and if I have 4 neighbors, so it will have 4 bonds and so on and so forth, right, and that will be equal to total number of AB bonds, because in each there will be an A atom associated, and 2 times AA bonds, because if I have a A atom here I will count, and if that also happens to be an A atom, for that also I will count towards this bond. So, there are twice the number of bonds when there are AA, right. So, this will be. So, how did we get this? So, we said the total number of A atoms and their coordination number at every site. So, that should be the total number of A bonds, and some of them are made with B and some of them are made with A itself. So, that is how we got it. In a similar fashion, so from here you can get that what is PAA? PAA is nothing but NAZ by 2 minus PAB by 2. In a similar fashion, you can write NB times Z will be equal to PAB plus 2 PBB. Why? Because there are total number of B atoms NB, and if Z is the coordination number, there should be NBZ total B bonds, B atoms associated with these bonds, and they are, some of them are AB bonds, some of them are BB bonds. So, that implies PBB is again NBZ by 2 minus PAB by 2. Okay. Now, we can write the total energy E in terms of these bond energy. So, what do I get? I get E equal to PAB EAB plus PAA can be replaced by NA Z by 2 minus PAB by 2 multiplying EAA plus NB Z by 2 minus PAB by 2 multiplying EBB. So, let us expand, and so we will have PAB EAB and minus PAB by 2 EAA minus PAB by 2 EBB. So, we can write that as PAB into EAB minus EAA plus EBB by 2. So, this is all the terms, and then of course, there are these plus NA Z by 2 EAA plus NA NB Z by 2 EBB. Okay. Now, NA Z by 2 EAA and NB Z by 2 EBB are nothing but the energy of the pure A and pure B. So, if we are interested in delta E, which is the E minus whatever energy you had for the pure material that you have taken together and put to form this mixture, then we know that that should be this quantity subtracted. So, NaZ by 2 EAA minus NBZ by 2 EBB. So, that is basically gives you PAB EAB minus EAA plus EBB by 2. Okay, now, so if we can write PAB, then we have delta E, which is what was written as omega XA XB. So, we need to calculate PAB, then we are through. So, we can get an expression. So, how do we get PAB? For getting PAB, we are going to assume that the sites are occupied randomly. Okay. Now, if suppose you have only A atoms, the probability of occupancy of any site is 100% for A. If you have only B atoms, of course, it is 100% for B. If you have any fraction, suppose 50% of the atoms are A atoms, then there is 50% probability that any given site will be occupied by A atom. In other words, if I want to know what is the probability that a given site is going to form a bond of the type AB, PAB. So, what do? I take two sites and then I find out the probability of this is A and this is B, that will form a AB bond, or this is A and this is B. What is the probability of this is A? That is given by XA. What is the probability that this is B? That is given by XB plus this is, say, in other words, 2 times XA XB is the probability that any given site is actually occupied, any given pair of sites will actually have a bond PAB. In a similar fashion, you can show that PAA is nothing but XA squared and PBB is actually XB squared. So, you add all these probabilities XA squared plus XB squared plus 2 XA XB, which is nothing but XA plus XB whole squared. XA plus XB is 1, so that is equal to 1. So, the total probability becomes 1. So, our probability calculation is okay. So, we are going to take that this is the probability that the occupancy is that quantity, but that is not the only thing. we also have to, so there are going to be n Avogadro number of sites, okay. So this is the probability, and for each site there are z bonds, and then we are considering pairs, so we have to divide by 2. So this quantity is basically the total number of AB bonds, okay. So this 2 is going to go away, so let us substitute, then we get the expression that delta E is nothing but the number of AB bonds, which is given by XA, XB, N0, Z times EAB minus EAA plus EBB by 2 is basically the change in energy, delta E mix is what how we defined, and this was written as omega XA XB, which implies that omega, the regular solution parameter, is nothing but N0 times Z times EAB minus EAA plus EBB by 2. Okay. So this is how the regular solution parameter is related to the Avogadro number, the number of nearest neighbors in the given crystal structure, so which could be 6 or 8 or 12 depending on what type of cubic system, for example, you are assuming, and this is nothing but on the average how costly or cheap is an AB bond with respect to AA BB bonds. That is, if you break one AA, one BB and make 2 EAB bonds, then how much is the change in energy. So if this is 0, then that is ideal solution, omega is 0. If this is positive or negative, then the system would prefer phase separation or ordering. So this is what we looked at. So this is how one derives the regular solution parameter in terms of these basic quantities. Thank you.